So hello friends, this is Jayaraj from Government Women's Polytechnic Holenarasipura, welcoming you all to this 5th session of Unit 4 of Hydraulics and Pneumatics, that is hydraulics machines. So in our last class we were discussing centrifugal pumps and we had discussed in detail about the construction and working of centrifugal pump, and we have few terminologies left in this centrifugal pump discussion which we will be continuing it today. So before moving on to the terminologies of centrifugal pump, we will be looking into a brief recap of previous session, and later we'll be moving on our discussion to some terminologies of centrifugal pump, and we'll be working out a simple worked example on centrifugal pump also. Later we'll be shifting our discussion to a classification, the next type of pump, that is the positive displacement pump. So one important type of positive displacement pump, that is the reciprocating pump. We'll be focusing our discussion on the reciprocating pump. We'll be seeing the working principle and construction of reciprocating pump. We'll be looking into various terminologies in order to find out the efficiency, discharge, etc. of the reciprocating pump, and we'll be working out a few worked examples in order to complete the chapter on pumps. So in our last class we discussed centrifugal pump. So the basic principle that lies behind a centrifugal pump that we have seen. So the basic principle here is the centrifugal force. So we have the impeller in a pump, so which has the radially curved vanes, radially backward curved vanes. So the water enters them along the axis of the shaft and passes through the blades, and it is thrown away by the centrifugal force, the rotation. This is the direction of rotation of the impeller. The water gliding through or passing through these blades will be thrown out by the blades at certain velocity. So because this water particles acquires a centrifugal force, so which are received by the casing. So different types of casing we have seen in our last class itself. A simplest type is the volute casing, which is of continuously increasing cross-sectional area. So the area of the cross section continuously or gradually increases in order to increase the pressure of the water that is being pumped. So the water continuously coming out from the impellers reach the casing, and finally the pressure of the water gets increased by this volute casing. All the velocity energy is just converted into pressure energy and leaves the pump into the delivery line at higher pressure. So this was the fundamental concept behind the centrifugal pump, and let us try to extend the discussion on centrifugal pump. We had learned a few terminologies in our last class. Let us say this is the suction pipe. So we had learned that this is the sump from which water is being pumped. So this is the eye of the impeller, or the center point of this impeller through which the water enters. See, the distance between the surface of the water from the sump to the center of the pump was called as the static head, or suction head it is called as. So next, the delivery head, that is the distance from the center point of the pump to the level of water in the tank. Suppose the water is being pumped into the tank, so this is the level of water in the tank. So up to the distance till here is called as the delivery head. See, both combined together was called as the static head. So this was called as the static head. So combination of the suction head and the delivery head was called as the static head. And we discussed the monometric head, so which had monometric head, which was a combination of all the heads. So the work that has to be done by a pump in order to complete its task, that is, I want to supply water from the sump till the tank. So what are all the heads that a pump has to supply in order to do this work, do the work satisfactorily? That is called as the monometric head. It has the suction head plus delivery head plus the losses. When we say losses, the losses that occur in the suction side as well as in the delivery side, maybe it may be a frictional losses or because of the bends, etc. So those losses and the velocity component, that is the velocity with which the water has to be supplied. So that also will be taken care by this manometric head. This is the total head that the pump has to supply in order to satisfy its requirement. So that was called as the manometric head. So let us move on to various efficiencies that are associated with the centrifugal pump. See, the first of the efficiencies that is associated with the centrifugal pump is the manometric efficiency. So the manometric efficiency, we have understood the manometric head. First of all, the manometric head is nothing but the ratio of the manometric head over the head imparted by the impeller to the water. That is the manometric efficiency. It is defined as the ratio of the manometric head over head imparted by the impeller to the water. So we know what is the manometric head. It is given by the capital HM. So that is the manometric head. Head imparted by the impeller to the water is nothing but the work done by the impeller on the water. So whose equation we already had learned. It is a product of the whirl velocity and the tangential velocity of the impeller over the acceleration due to gravity. We have sent it to the numerator. So this is nothing but the head imparted by the impeller to the water or work done by the impeller to the water. So the manometric efficiency is defined as the ratio of manometric head over the work done by the impeller on water. So that is given by this equation. So this equation has been reduced in order to get this equation. So using this equation, we'll be able to find out the manometric efficiency. The next form of efficiency is the mechanical efficiency. Since much of the components are of mechanical in nature, so there is an efficiency associated called as mechanical efficiency. So wherein the losses may be occurring because of friction or various other reasons that deviates from the theoretical power that can be given to the water. So mechanical efficiency is defined as the ratio of power at the impeller over the power at the shaft. So it is, suppose this is the pump. So the power that is inputted to this pump is the power at the shaft that is given by the motor. So the numerator is power at the impeller, that is the power that is being given to the impeller. So R, that is the work done by the impeller on the water. Both are same. Power at the impeller is nothing but work done by the impeller on water. So which is given by this equation, VW2, whirl velocity at the exit into multiplied by the tangential velocity of the impeller over the acceleration due to gravity. W is nothing but the specific weight of the water. So divided by the shaft power, that is the input power to the shaft. The power that has been supplied to the shaft is called as the shaft power. So this is the mechanical efficiency equation. So the derivation part we will not be looking at. So this is the simplest expression which we can use it in order to solve few numericals. Then finally we have the overall efficiency. Overall efficiency is nothing but the combination of the mechanical efficiency and the manometric efficiency. It can be also defined as the product of mechanical efficiency and the manometric efficiency. So overall efficiency is defined as the power output of the pump divided by the power that has been supplied into the pump. So power that has been supplied into the pump is nothing but the power at the shaft, power that is given to the shaft. So next, the numerator is power output of the pump. The power output of the pump, we already know it is nothing but the manometric head. So power output, final power output that we are getting from the pump is the manometric head. So this manometric head divided by the shaft power, that is the basic input power that we are giving to the shaft. So when this is solved, we'll get the efficiency known as the overall efficiency. Overall efficiency is also given by the product of manometric efficiency and mechanical efficiency. MAN is manometric efficiency and NM is the mechanical efficiency. So that will give us the overall efficiency. Let us look at a simple worked example. The internal and external diameter of the impeller of a centrifugal pump are 200 mm and 400 mm. So we had learned that the impeller has two diameters. See, impeller has blades on it. So the inner portion diameter is the D1, the outer portion diameter is D2. So that is being given in the problem. The internal and external diameter of the impeller of a centrifugal pump is 200 mm and 400 mm. So which we have to convert it into meters respectively. The pump is running at RPM, N is equal to 1200 RPM. The vane angles of the impeller at inlet and outlet are 20 and 30 degrees respectively. The vane angles of the impeller at inlet and outlet. So what this means? So vane angle is nothing but the blade angle. The vane angle at the inlet and outlets are nothing but theta and phi. So we had learned the angle theta and phi is nothing but the angle made by the relative velocity at the inlet and the angle made by the relative velocity at the outlet. So phi is the angle made by the relative velocity at the exit, and theta is the angle made by the relative velocity at the inlet. So they are called as the vane angles. So theta is the vane angle at the inlet, that is 20 degree. So and phi is the vane angle at the outlet, that is 30 degrees respectively. The water enters the impeller radially. So when we see this term radially, so when we say the word radially, so it means to say that alpha is equal to 90 degree. Alpha is 90 degree means the absolute component of the velocity v1 is perpendicular. It is perpendicular. So when we say this is perpendicular, v1 is equal to vf1, velocity of the flow at the inlet. So just because there is no horizontal component or there is no component of absolute velocity along the direction of motion, so vw1 will be equal to 0. So when we say the flow is entering radially, so it means so much, it gives us so much of information. When the water enters impeller radially, alpha is equal to 90 degrees. So when alpha is 90 degree, v1 will be equal to vf1, and the component of the vw1 will be equal to 0. So this is our observation from this word radially, and the velocity of the flow is constant. So determine the work done by the impeller per unit weight of the water. So we have to find out the work done by the impeller per unit weight of water. So work done by the impeller was, we understood the equation. So work done is given by the equation vw2 into u2 divided by g. So this was the equation in order to find out the work done by the impeller per unit weight of the water. So we have to find out the whirl velocity at the exit and the tangential velocity of the impeller u2, then we'll be able to find out the work done by the impeller. So given are the diameters, D1 internal diameter of the impeller is 0.2 meters, D2 outside diameter is 0.4 meters. 400 mm has been reduced to 0.4 meters. So N speed of the impeller is 1200 rpm. So inlet angle, that is inlet vane angle, theta is 20 degree, phi is 30 degrees. So alpha is 90 degree just because the water is entering radially. So next vw1 whirl velocity at inlet is 0. So we have already discussed this now. So for a centrifugal pump, velocity of the flow at the inlet will be equal to velocity of the flow at the exit, vf1 equal to vf2. So this is the typical velocity triangle for this condition. So here we are able to see v1 is entering radially. So the water is entering radially because alpha is equal to 90 degrees. So water enters radially means alpha is 90 degree. Here we are able to see v1 is perfectly vertical. When v1 is completely vertical, it will not have any horizontal component. So that is vw1 will be definitely equal to 0. So it will not have any horizontal component, and also the vertical component vf1 of v1, both are equal because v1 is already vertical, it is at 90 degree, hence it is equal to vf1. And we know that relative velocity component at an angle theta, so theta is given, the theta is 20 degrees, and at the outlet, this is the velocity triangle we are seeing. So the relative velocity at an angle phi, which is given as 30 degree. So vf2 and all other things will be able to find out. So here we have the velocity at the exit, absolute velocity at the exit v2 at an angle beta. So next we have the relative velocity at an angle phi, so with the tangential speed at the exit and the whirl velocity at the outlet. So we have to find out this whirl velocity at the exit and the tangential velocity at the of the impeller at the exit. So after finding these two, we'll be able to find out the work done by the impeller. So we have U1 was given by the formula pi d1 into n by 60. So pi d1 into n divided by 60. So d1 was 0.2 meters. So speed of the impeller was 1200 rpm. So after calculation we are obtaining U1 as 12.56 meters per second. So formula for U2 is pi d2 into n divided by 60. So d2 was given in the problem, it is 0.4 meters multiplied by the revolution 1200 rpm will give us the speed U2 at the exit as 25.13 meters per second. So we know tan theta is equal to Vf1 by U1. So here we are able to find out from the inlet conditions. So applying tan theta here, so applying tan theta, so we are getting Vf1 divided by U1. So that is opposite by adjacent side. So Vf1 divided by adjacent is U1. So we know the value of theta. So we have to find out the value of Vf1 here. We know U1 from this calculation. We know theta. We have to find out the value of velocity flow at the inlet. So realigning this equation, Vf1 equal to U1 into tan theta. So we know the value of U1 and tan theta. So U1 is 12.56, tan 20 degree. So after calculation, we are obtaining Vf1 as 4.57 meters per second. And in centrifugal pump, we know the condition, velocity of the flow at the inlet is equal to velocity of the flow at the exit. So Vf1 and Vf2 are one and the same. So now by calculating Vf1, I am able to say what is Vf2. So Vf2, I know Vf2 here, I know the angle phi, so I know the value of U2. So then I will be able to find out what is Vw2, which I am interested in. So for this, I need to find out this side distance, that is, let us say x or whatever. So applying tan phi here, once again applying tan function, I'll be able to find out Vf2 and this value of x. So after finding this value of x, I'll be able to subtract this from the value of U2 in order to obtain the viral velocity at the exit. So applying tan phi at the exit side, so tan phi is equal to opposite by adjacent side. So I represented this as x, or simply I can write U2 minus Vw2. So this is represented by U2 minus Vw2. So U2 nalli nanu Vw2 na minus madidre ನನಗೆ ಈ ಡಿಸ್ಟೆನ್ಸ್ ಸಿಗುತ್ತೆ. So applying tan phi opposite by adjacent side, opposite is Vf2. Vf2 ನನಗೆ ಗೊತ್ತು, Vf2 was equal to Vf1. So I know the value of phi as 30 degrees, so I can easily find out the distance of this side of the triangle. So realigning the equation to find out Vf2, so by cross multiplying tan phi into U2 minus Vw2. So applying tan function here, I'll be able to find out the value of whirl at the exit, that is 17.215 meters per second. Now I know the value of Vw2 and U2, so then I can straight away move to the final equation in order to find out the work done by the impeller on the water per unit weight of water. So that is given by equation Vw2 into U2 divided by G. So applying all the values, so I am obtaining the answer as 44.1 Newton meter per Newton. So that is per Newton in term, because we are finding out the work done per unit weight of the water. So this is the answer. So next concept is priming. So what exactly is priming? Let us see. So priming is a simple process of removing air present in the suction side of the pump. So in the pump we have mainly, so let us say this is the pump, we have the suction pipe and the delivery pipe. So suppose this is suction, we want to remove the air present in this suction side. See, if this is the eye of the impeller, I want to remove the air present in the casing as well as the suction pipe and also part of the delivery pipe. Let us say up to here, I want to remove the air that is present inside. So what we do, so generally in our day-to-day life, we do priming by just filling water inside the pump. So we are filling water in order to remove the air. So we fill water through the delivery line. So in order to fill the complete suction line, the complete casing and part of the delivery line with water in order to remove the air. But air idre ಏನು disadvantage? So air ಯಾಕೆ ಇರಬಾರ್ದು ಪಂಪ್ ನಲ್ಲಿ? So air na remove ಮಾಡೋ ಕೆಲಸನೇ priming, but air ಯಾಕೆ ಇರಬಾರ್ದು? See, when this pump is completely filled with air, let us say the pump is completely filled with air. So the suction side is, the pipe is completely filled with air. So I switch on the pump. So when the pump starts rotating, a low pressure region is created here. Because the air is completely present in this region, this low pressure region is developed in terms of head of air. Head of air andre pressure in terms of air. So ಈ air, ಈ head of air ಅನ್ನೋದು ತುಂಬಾ ಕಡಿಮೆ ಇರುತ್ತೆ. ಸೊ ಈ ತುಂಬಾ ಕಡಿಮೆ ಇರುವಂತಹ ಈ ಪ್ರೆಷರ್ ನೀರನ್ನ ಸಂಪ್ನಿಂದ ಅಥವಾ ಟ್ಯಾಂಕ್ ನಿಂದ ಸಕ್ ಮಾಡಕ್ಕೆ ಆಗೋದಿಲ್ಲ. ಸೊ ಬಿಕಾಸ್ ದ ಹೆಡ್ ಡೆವಲಪ್ಡ್ ಇಸ್ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಹೇರ್ ವಿಚ್ ಇಸ್ ವೆರಿ ವೆರಿ ಲೆಸ್ಸರ್. ಸೊ ನಾವೇನ್ ಮಾಡ್ಬೇಕು, ಹೆಡ್ ಡೆವಲಪ್ಡ್ ಮಸ್ಟ್ ಬಿ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ವಾಟರ್. ಸೊ ಹಿಯರ್ ದ ಪ್ರೆಷರ್ ಹೆಡ್ ಡೆವಲಪ್ಡ್ ಮಸ್ಟ್ ಬಿ ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ವಾಟರ್. ಸೊ ಅದು ಅವಾಗ ಮಾತ್ರನೇ ನೀರ್ನ ಅದು ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ ಫುಲ್ ಮಾಡಕ್ಕೆ ಸಾಧ್ಯ. ಸೊ ಅದಕ್ಕೆ ನಾವೇನ್ ಮಾಡ್ತೀವಿ, ವಿ ಫಿಲ್ ದಿ ಕಂಪ್ಲೀಟ್ ಸಕ್ಷನ್ ಲೈನ್. ಈ ಸಕ್ಷನ್ ಲೈನ್ ನ ಮ್ಯಾನುವಲ್ ಆಗಿ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಫಿಲ್ ಮಾಡ್ತೀವಿ. ಕೇಸಿಂಗ್ ನ ಕಂಪ್ಲೀಟ್ ಆಗಿ ನೀರಿನಿಂದ ಫಿಲ್ ಮಾಡ್ತೀವಿ. ಅಂಡ್ ಪಾರ್ಟ್ ಆಫ್ ದಿ ಡೆಲಿವರಿ ಲೈನ್ is filled with water. Then when the pump is switched on, the head completely water is present in the suction line. Once pump starts rotating and a negative and a suction pressure is created here, the pressure created is in terms of head of water. So and easily the water gets sucked from the tank. So the main important reason why we do priming is we want to develop a head which is in terms of head of water. So before starting the pump, we are removing the air, we are filling the suction pipe casing and part of the delivery pipe with water. The head generated in terms of meters of air is not enough to suck the water. The head generated here will be in terms of heads of air, so which is not enough in order to suck the water from the sump. Hence we have to fill water completely into the suction line, and therefore we are developing the pressure in terms of head of water. So thereby the suction takes place very efficiently. So if the pump is run with completely air inside for prolonged time, so it will lead to overheating and it may lead to damage of the pump. So hence priming has to be done, so in order to avoid the failure of the pump. So next concept is cavitation. So cavitation is a phenomenon that occurs in the suction side. So when the pressure drops below the vapor pressure, so when the pressure in the suction side drops below the vapor pressure, so a problem called as a cavitation occurs. So what exactly is this cavitation? So cavitation is formation of cavities on the blades or inner surface of the casing. So cavities maybe leading to erosion or pitting corrosion. So ನಮ್ಮ ಕೇಸಿಂಗ್ ನ ಒಳಭಾಗ ಅಥವಾ ಇಂಪೆಲ್ಲರ್ ನ ಬ್ಲೇಡ್ಸ್ ಗಳು ಕೊರೋಷನ್ ಇಂದ ಹಾಳಾಗೋದು, ಪಿಟ್ಟಿಂಗ್ ಆಗೋದು, ಕ್ಯಾವಿಟೀಸ್ ಫಾರ್ಮ್ ಆಗೋದು, ಆ ಬ್ಲೇಡ್ ಸರ್ಫೇಸ್ ಗಳು ಹಾಳಾಗೋದನ್ನೇ ನಾವು ಕ್ಯಾವಿಟೇಷನ್ ಅಂತ ಹೇಳಿ ಕರಿತೀವಿ. ಸೊ ಈ ಕ್ಯಾವಿಟೇಷನ್ ಆಗೋದು ಸಕ್ಷನ್ ಸೈಡ್ ನಲ್ಲಿ ಪ್ರೆಷರ್ ತುಂಬಾ ಡ್ರಾಪ್ ಆದಾಗ. ಸೊ ಸಕ್ಷನ್ ಸೈಡ್ ನಲ್ಲಿ ಪ್ರೆಷರ್ ಎಷ್ಟರ ಮಟ್ಟಿಗೆ ಡ್ರಾಪ್ ಆದಾಗ, ವೇಪರ್ ಪ್ರೆಷರ್ ನ ಕೆಳಗೆ ಅದು ಡ್ರಾಪ್ ಆದಾಗ. ಸೊ ದೇರ್ ಇಸ್ ಅ ಪ್ರೆಷರ್ ಕಾಲ್ಡ್ ವೇಪರ್ ಪ್ರೆಷರ್. ಸೊ ಲೆಟ್ ಅಸ್ ಟ್ರೈ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ವಾಟ್ ಇಸ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್. ಸಪೋಸ್ ಐ ಹ್ಯಾವ್ a container filled with water, I starts heating it. So ಇದನ್ನ ನೀರನ್ನ ಬಿಸಿ ಮಾಡ್ತಾ ಇದ್ದಂಗೆ ನೀರನ್ನ ಆವಿ ಜನರೇಟ್ ಆಗುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ಅ ಕ್ಲೋಸ್ಡ್ ಕಂಟೈನರ್. ಈ ವಾಟರ್ ಪಾರ್ಟಿಕಲ್ಸ್ ನೀರಾವಿ ಏನಾಗುತ್ತೆ, ಈ ನೀರಿನ ಸರ್ಫೇಸ್ ಮೇಲೆನೆ ಕಲೆಕ್ಟ್ ಆಗಿರುತ್ತೆ. ಸೊ ಕೆಲವು ಟೈಮ್ ಆದ್ಮೇಲೆ ಏನಾಗುತ್ತೆ, ಈ ನೀರಿನ ಆವಿ ಪಾರ್ಟಿಕಲ್ಸ್, ವಾಟರ್ ಪಾರ್ಟಿಕಲ್, ಸ್ಟೀಮ್ ಪಾರ್ಟಿಕಲ್ ಏನಾಗುತ್ತೆ, ಕಂಡೆನ್ಸ್ ಆಗಿ ಮತ್ತೆ ಅದು ನೀರಾಗಿ ಕನ್ವರ್ಟ್ ಆಗಿ ಸರ್ಫೇಸ್ ಜೊತೆ ಸೇರ್ಕೊಂಡ್ಬಿಡುತ್ತೆ. ಸೊ ಈ ನೀರು ವಾಟರ್ ಪಾರ್ಟಿಕಲ್ಸ್ when they condense back to water, they exert pressure. All water particles start exerting a pressure on the surface of the water, which is called as the vapor pressure. So water at this pressure is called as the vapor pressure. When nama suction side nalli, suppose this is the suction side, when the pressure of the water at the suction side falls below the vapor pressure, ಈ ವೇಪರ್ ಪ್ರೆಷರ್ ಗಿಂತ ಕಡಿಮೆ ಆದ ಪ್ರೆಷರ್ ಇಲ್ಲಿ ಡೆವಲಪ್ ಆದಾಗ ಏನಾಗುತ್ತೆ, ನಾವು ಯಾವುದೇ ಬಿಸಿ ಮಾಡೋ ಅವಶ್ಯಕತೆನೇ ಇಲ್ಲ, ನೀರು ತನ್ನಿಂದ ತಾನೇ ಬಾಯ್ಲ್ ಆಗಕ್ಕೆ ಶುರು ಮಾಡುತ್ತೆ. ವಾಟರ್ ವಿಲ್ ರೀಚ್ ಇಟ್ಸ್ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಅಟ್ ದಿಸ್ ವೇಪರ್ ಪ್ರೆಷರ್, ಅಂದ್ರೆ ತುಂಬಾ ಅತಿ ಕಡಿಮೆ ಆದ ಪ್ರೆಷರ್ ನಲ್ಲಿ ಈ ಬಾಯ್ಲ್ ಆದಂತ ವಾಟರ್ ಸ್ಟೀಮ್ ಪಾರ್ಟಿಕಲ್ಸ್, ಈ ವಾಟರ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಏನಾಗುತ್ತೆ, ಅಟ್ ರ್ಯಾಪಿಡ್ ಪೇಸ್ ಕಮ್ಸ್ ಅಂಡ್ ಹಿಟ್ಸ್ ದಿಸ್ ಬ್ಲೇಡ್ಸ್ ಆಫ್ ದಿ ಇಂಪಲರ್. ಮತ್ತೆ ಈ ಒಳ ಕೇಸಿಂಗ್ ನೆಲ್ಲ ಏನಾಗುತ್ತೆ, ಒಂದು ರ್ಯಾಪಿಡ್ ಸ್ಪೀಡ್ ನಲ್ಲಿ ಬಂದು ಅದನ್ನ ಹಿಟ್ ಮಾಡಿ it collapses into water particles once again. So ಈ ಒಂದು process ನಲ್ಲಿ ಏನಾಗುತ್ತೆ, so inner portion of the casing, ಈ ಕೇಸಿಂಗ್ ನ ಒಳಭಾಗ ಬ್ಲೇಡ್ಸ್ ಗಳ ಸರ್ಫೇಸ್ ಏನಾಗುತ್ತೆ, they start forming cavities, ಹಾಳಾಗಕ್ಕೆ ಶುರು ಮಾಡುತ್ತೆ. ಇದನ್ನೇ ನಾವು cavitation ಅಂತ ಹೇಳಿ ಕರಿತೀವಿ, which must be avoided for a prolonged life of the pump. So pump ನ ಲೈಫ್ ಟೈಮ್ ನ ನಾವು ಜಾಸ್ತಿ ಮಾಡ್ಬೇಕಂದ್ರೆ we have to avoid this cavitation. So So this has to be completely avoided for sufficient lifetime of the pump. So water starts boiling, forming vapor bubbles. So water boil agak shuru madade yavaga pressure bandu vapor pressure ginta kadime drop adaga. So these bubbles strike the blades with higher velocity and hence forms the cavities on the blades. Blades mele cavities sanna sanna cavity galagi form agate. So ee cavity annadu blade gal ಮೇಲೆ ಮಾತ್ರ ಅಲ್ಲ ಕೇಸಿಂಗ್ ನ ಕೂಡ ಅದು ಡಿಸ್ಟರ್ಬ್ ಮಾಡ್ತವೆ. So this leads to corrosion and pitting. So corrosion and pitting, so form of corrosion, so which leads to prolonged corrosion. So corrosion ಮತ್ತೆ ನಿಲ್ಲದೆ ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ ಬ್ಲೇಡ್ ಮತ್ತೆ ಕೇಸಿಂಗ್ ಸರ್ಫೇಸ್ ಗಳನ್ನ ಹಾಳು ಮಾಡುತ್ತೆ. So in order to avoid these things, we have to ensure that the pressure at the suction doesn't fall below the vapor pressure, and also the blades and the casing must be designed with suitable corrosion resistance material like aluminum, stainless steel, etc. So next we have the centrifugal pump at multi-stages, at different stages. So when we are not happy with a single impeller, we employ 2 or more impellers, which is called as the multi-stage centrifugal pump. So a multi-stage centrifugal pump is used in order to produce a higher head. I want a higher pressure, and when I want high discharge. So under both these conditions, we use the centrifugal at different stages of centrifugal pump. So centrifugal pump consisting of 2 or more impeller is called as the multi-stage. Multi-stage is done in order to produce a higher head or higher pressure and higher discharge. So the reason for not having a larger size impeller, see, when we want a higher head or higher pressure, I can use a larger pump also. ನನಗೆ ಪ್ರೆಷರ್ ಜಾಸ್ತಿ ಬಿದ್ದಾಗ ಅತಿ ದೊಡ್ಡದಾದಂತಹ ಒಂದು ಪಂಪ್ ನ ಕೂಡ ನಾನು ಬಳಸಬಹುದು, ಬಟ್ ದಟ್ ಈಸ್ ನಾಟ್ ಎಕನಾಮಿಕಲ್ ಅಂಡ್ ನಾಟ್ ಎಫಿಷಿಯಂಟ್. ಯಾಕೆ ಅಂತ ಹೇಳಿದ್ರೆ ಲಾರ್ಜರ್ ಸೈಜ್ ಆಫ್ ದಿ ಇಂಪೆಲ್ಲರ್, ದೊಡ್ಡ ಸೈಜ್ ಆದಂತಹ ಇಂಪೆಲ್ಲರ್ ಅತಿ ಕಾಸ್ಟ್ಲಿ ಕೂಡ ಆಗುತ್ತೆ, ಮತ್ತೆ ಬ್ಲೇಡ್ ನ ನಾನು ಅತಿ ದೊಡ್ಡದಾಗಿ ಅಂದ್ರೆ ಜಾಸ್ತಿ ಬಿಯಾಂಡ್ ದಿ 45 ಡಿಗ್ರಿ ನಾನು ಆಂಗಲ್ ಕೊಡೋದಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ, ಬಿಕಾಸ್ ಇಟ್ ರಿಡ್ಯೂಸಸ್ ಎಫಿಷಿಯನ್ಸಿ ಆಫ್ ದಿ pump. And the single impeller can be, in practice, single impellers are used up to head of 50 meters only. 50 meter head ge maatrane nanu single impeller pump na ಬಳಸೋಕೆ ಸಾಧ್ಯ. So therefore I employ multi stages, ಒಂದಕ್ಕಿಂತ ಹೆಚ್ಚಾದಂತಹ ಇಂಪೆಲ್ಲರ್ ಗಳನ್ನ ನಾನು ಬಳಸ್ತಾ ಹೋಗ್ತೀನಿ in order to get high discharge and the higher head. So multi stage pump ಅಂತ ಹೇಳಿದಾಗ we have 2 stages, that is, one is pumps in series and pumps in parallel. So pumps in series, so here in this picture we are able to see pumps, 2 pumps are connected in series. So they are mounted on the same shaft, ಒಂದೇ shaft ನಿಂದ ಅದಕ್ಕೆ they are deriving power. So when pumps are connected in series, let us take an example. See, one pump gets the input from the sump, so it raises its pressure. It is raising its pressure to certain level, let us say 50 heads, and then it is giving the delivery into the next inlet of the next pump. So ಒಂದು ಪಂಪ್ ನಿಂದ ಬಂದಂತಹ ಔಟ್ಲೆಟ್ ಇನ್ನೊಂದು ಪಂಪ್ ಗೆ ಇನ್ಲೆಟ್ ಆಗಿ ಹೋಗ್ತಾ ಇದೆ. ಸೊ ಇಲ್ಲಿ 50 ಹೆಡ್ಸ್ ಡೆವಲಪ್ ಆಗಿರೋದು. ಸೊ ನೆಕ್ಸ್ಟ್ ಸ್ಟೇಜ್ ನ ಪಂಪ್ ನಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಇನ್ನೂ ಹೈಯರ್ ಹೆಡ್ ಗೆ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ಆಲ್ರೆಡಿ ಹೆಡ್ ಜಾಸ್ತಿಯಾಗಿ 50 meters ಗೆ ಡೆವಲಪ್ ಆಗಿದೆ. ನೆಕ್ಸ್ಟ್ ಸ್ಟೇಜ್ ನಲ್ಲಿ ಇಟ್ ಗೆಟ್ಸ್ ಡೆವಲಪ್ಡ್ ಟು ಹೈಯರ್ ಸ್ಟೇಜ್ ಆಫ್ ಹೆಡ್, ಮೇ ಬಿ ಲೆಟ್ ಅಸ್ ಸೇ 80 meters or so. So this is the advantages when by connecting the pumps in series. So the overall, the final head can be the multiple of the monometric heads of individual heads. Suppose one pump na maximum head, that is monometric head, is let us say HM. Now I have n number of impellers attached in series. So n number of impellers anta helidre 10 15 esto. So when I multiply the head of one impeller with the number of impellers totally attached, so I'll be getting the total head developed by the pump. So to summarize this, so pumps are connected in series in order to obtain higher pressure ಅಥವಾ higher head. ನನಗೆ ಯಾವಾಗ ಅತಿ ಹೆಚ್ಚಾದ ಪ್ರೆಷರ್ ಬೇಕೋ ಅವಾಗ ನಾನು ಪಂಪ್ ಗಳನ್ನ ಸೀರೀಸ್ ಆಗಿ ಕನೆಕ್ಟ್ ಮಾಡ್ಕೊಳ್ತೀನಿ. ಸೊ ಒಂದರ ಔಟ್ಲೆಟ್ ಬಂದು ಇನ್ನೊಂದಕ್ಕೆ ಇನ್ಲೆಟ್ ಆಗುತ್ತೆ, ಸೊ ಪ್ರೆಷರ್ ಏನಾಗುತ್ತೆ, ದುಪ್ಪಟ್ಟಾಗುತ್ತೆ, ಸೊ ಇನ್ನೂ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ now let us see a diagram, so wherein we are seeing the pumps connected in series. So here we have the impeller, many number of impellers connected to a common shaft. ಇಲ್ಲಿ ನಾವು ನೋಡಬಹುದು. ಸೊ ಇಲ್ಲಿ ಒಂದು ಸೆಕ್ಷನ್ ಲೈನ್ ಇದೆ, ಒಂದೇ ಡೆಲಿವರಿ ಲೈನ್ ಇದೆ, ನೀವು ನೋಡಬಹುದು. ಸೊ ಒಂದು ಇಂಪೆಲ್ಲರ್ ನ ಔಟ್ಲೆಟ್ ಏನಾಗುತ್ತೆ, ಇನ್ನೊಂದು ಇಂಪೆಲ್ಲರ್ ಗೆ ಇನ್ಲೆಟ್ ಆಗುತ್ತೆ. ಸೊ ಇಲ್ಲಿ ನಾವು ನೋಡ್ತಾ ಇದೀವಿ. ಸೊ ದ ಮ್ಯಾನಿಫೋಲ್ಡ್, ಸಿ ದ ಔಟ್ಲೆಟ್ ಮ್ಯಾನಿಫೋಲ್ಡ್ ಆಫ್ ದಿಸ್ ಇಂಪೆಲ್ಲರ್ ಬಿಕಮ್ಸ್ ದಿ ಇನ್ಲೆಟ್ ಫಾರ್ ದಿ ನೆಕ್ಸ್ಟ್ ಪಂಪ್. ಸೊ ಇದರ ಔಟ್ಪುಟ್ ಇಲ್ಲಿಗೆ ನೆಕ್ಸ್ಟ್ ಬರುತ್ತೆ, ಥರ್ಡ್ ಸ್ಟೇಜ್ ಗೆ. ಥರ್ಡ್ ಸ್ಟೇಜ್ ಫೋರ್ತ್ ಸ್ಟೇಜ್ ಹೋಗುತ್ತೆ. ಫೋರ್ತ್ ಸ್ಟೇಜ್ ನ ಔಟ್ಪುಟ್ ಬಂದು ಫಿಫ್ತ್ ಸ್ಟೇಜ್ ಗೆ ಹೋಗಿ ಫೈನಲಿ there is a one output coming out from this multi stage centrifugal pumps, that is pumps connected in series, has the higher pressure. So ಒಂದು ಇಂಪೆಲ್ಲರ್ ನ ಕೈಯಲ್ಲಿ ಕೊಡದೇ ಇರುವಂತಹ ಶಕ್ತಿ ಈ 5 ಇಂಪೆಲ್ಲರ್ಗಳು ಒಟ್ಟು ಸೇರಿ, so it has increased the pressure of the water to a very higher level. So next we'll see pumps in parallel. So pumps are connected in parallel when we want more discharge. ನನಗೆ ಅತಿ ಹೆಚ್ಚಾದಂತಹ ಫ್ಲೋ ಬೇಕು ಅಂದಾಗ ನಾನು ಪ್ಯಾರಲಲ್ ಆಗಿ ಪಂಪ್ ನ ಕನೆಕ್ಟ್ ಮಾಡ್ಕೊಳ್ತೀನಿ. ಸೊ ಸೀರೀಸ್ ಅಲ್ಲಿ ನಾನು ಹೈಯರ್ ಹೆಡ್ ಬೇಕಾದಾಗ ಸೀರೀಸ್ ನಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡಿದೆ. ಸೊ ಪಂಪ್ಸ್ ನ ಪ್ಯಾರಲಲ್ ಅಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ ಯಾವಾಗ ಅತಿಯಾದ ಡಿಸ್ಚಾರ್ಜ್ ಬೇಕಾದಾಗ ನನಗೆ ಟು ಡೆವಲಪ್ ಎ ಲಾರ್ಜರ್ ಡಿಸ್ಚಾರ್ಜ್. ಸೊ ಡೆಲಿವರಿ ಆಫ್ ಈಚ್ ಪಂಪ್ ಎಂಟರ್ಸ್ ಎ ಕಾಮನ್ ಡೆಲಿವರಿ ಲೈನ್. ಸೊ ಅಲ್ಲಿ ನಾವು ಒಂದು ಪಂಪ್ ನ ಡೆಲಿವರಿ ಇನ್ನೊಂದು ಪಂಪ್ ಗೆ ಹೋಗೋದನ್ನ ನೋಡಿದ್ವಿ ನಮ್ಮ ಸೀರೀಸ್ ಪಂಪ್ ನಲ್ಲಿ. ಇಲ್ಲಿ ಸೊ ಈಚ್ ಇಂಪೆಲ್ಲರ್ ಇಸ್ ಸೆಪರೇಟ್. ಸೊ ಪ್ರತಿ ಒಂದು ಪಂಪ್ ಕೂಡ ಸೆಪರೇಟ್ ಆಗಿರುತ್ತೆ. ಆ ಪ್ರತಿ ಪಂಪ್ ನಿಂದ ಬಂದಂತಹ ಡೆಲಿವರಿ ಒಂದು ಕಾಮನ್ ಡೆಲಿವರಿ ಲೈನ್ ಗೆ ಕನೆಕ್ಟ್ ಆಗಿರುತ್ತೆ. ಸೊ ಈ ಕಾಮನ್ ಲೈನ್ ಗೆ ಬರ್ತಾ ಇರುವಂತದ್ದು ಏನ್ ಮಾಡುತ್ತೆ, ಸೊ ಕ್ಯೂ ನ ಜಾಸ್ತಿ ಮಾಡುತ್ತೆ. ದ ಡಿಸ್ಚಾರ್ಜ್ ಇಸ್ more, so discharge gets added up. So e pump ninda bandanತಹ discharge q1 gets added up to the discharge of the second pump. So third pump to discharge hige add agi, so the overall the final flow will be more, whereas the pressure is same. Pressure of all the impellers will be one and the same. The total discharge that is obtained, the total discharge qt is nothing but n times q. n is number of impellers. ಎಷ್ಟು ನಾನು ಇಂಪೆಲ್ಲರ್ ಗಳನ್ನ ಇಲ್ಲಿ ಹಾಕೊಂಡಿದ್ದೀನಿ, ಅದರ ಜೊತೆ ನಾನು ಒಂದು ಇಂಪೆಲ್ಲರ್ ಡಿಸ್ಚಾರ್ಜ್ ನ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿದಾಗ ಐ ವಿಲ್ ಬಿ ಗೆಟಿಂಗ್ ದಿ ಟೋಟಲ್ ಡಿಸ್ಚಾರ್ಜ್ ಆಫ್ ದಿಸ್ ಮಲ್ಟಿ ಸ್ಟೇಜ್ ಸೆಂಟ್ರಿಫ್ಯೂಗಲ್ ಪಂಪ್ಸ್ ಕನೆಕ್ಟೆಡ್ ಇನ್ ಪ್ಯಾರಲಲ್. ಸೊ n is the number of impellers. So we have reciprocating pump. So next, it is one of the type of positive displacement pump. So reciprocating pump converts the mechanical energy to hydraulic energy by a piston cylinder arrangement. We had seen that reciprocating pump is nothing but a positive confinement pump. It has a positive region wherein a fluid is arrested in this region and whose pressure will be increased by movement of wall. So here I have a fluid, let us say, so whose pressure will be increased by this piston cylinder arrangement. So this piston pushes this liquid and hence the pressure of this fluid rises. By reduction in the volume, it comes out at a higher pressure. So this is the fundamental concept behind this reciprocating pump. Mechanical energy is converted into hydraulic energy, so by piston cylinder arrangement. So used for a small quantity of fluid and larger pressure. So in our centrifugal pumps, we had seen that the pressure of the centrifugal pump is limited, whereas the discharge is very higher in a centrifugal pump, whereas in a reciprocating pump the discharge is lower but the pressure is very much higher. So this is the concept behind the reciprocating pump. So under this condition we'll be employing the pump. So when we need higher discharge, we are employing centrifugal pump. When we are requiring higher pressure but lower discharge, we can employ a reciprocating pump. So reciprocating pump has the following components. It has a cylinder with a piston rod, connecting rod, crank, suction pipe, delivery line, etc. So let us have a look at a simple video. So here we have a cylinder and piston attached to piston rod. So this is a piston rod attached to a piston within a cylinder arrangement. So piston rod is attached to a connecting rod. So the connecting rod itself is attached to a crank and a crankshaft. So this is rotated by a prime mover. It may be a motor or any other arrangement. So this is rotated. When this crank rotates, the connecting rod oscillates in order to move this piston rod inside and outside. So when it revolves by one complete revolution, there are two strokes happening. So one is inside and another one is outside. So one is extension, another one is called retraction. So here we are able to see the inlet pipe and we have the discharge pipe here. So when the piston is retracted backwards, so here the inlet line is connected to the sump, which is called as the water or it may be oil, whatever. So here we have the inlet valve or suction valve called as, and this is the delivery valve. So which is both are non-return valves. So suction, so only there will be flow from the sump to the cylinder and not vice versa. So and here there can be flow from cylinder to delivery line and not in the reverse way. So when the crank starts rotating, so here we are able to see This is the suction retraction stroke, or when the piston retracts, suction takes place. So the valve opens and the fluid enters the cylinder completely. So this is called as the suction stroke. So now the piston is completely retracted, valve opened, so oil completely fills inside the cylinder. So and next, during the next stroke, see, when it rotates by another 180 degree, first 180 degree retraction, that is suction stroke, next to 180 degree, so it will be what? Extension stroke. When the piston extends further, it pushes the liquid in order to reduce the volume, thereby increase the pressure. Because of increase in pressure, this delivery valve opens up. Here we are able to see delivery valve opens. The liquid in this region at higher pressure discharges into the discharge pipe. So this is the concept behind the single acting reciprocating pump. So we say single acting reciprocating reciprocating pump because the piston is in contact with only on its one side with the liquid. So here in this block diagram, we are able to see the piston cylinder arrangement with connecting rod attached to a crank. So when it revolves, see, when this crank revolves by 180 degrees, see, this complete rotation consists of 360 degrees, that is ABCD. So when the crank rotates from, let us say, from A, B to C, so when it go back to C, there is a retraction stroke for 180 degree, and when it travels from C to A, when it rotates from C to A, so there will be extension stroke. Extension stroke leads to increase of pressure, whereby the fluid attained in this region gets pushed to the delivery line. So we have all this components attached over here. So piston rod, connecting rod, crank, etc., delivery valve or the suction valve. So all these components makes into the working of single acting reciprocating pumps. So reciprocating pumps are classified according to action of water as single acting pump and double acting reciprocating pump. So we'll be seeing what is single acting and the double acting pump are according to number of cylinders. So we have single cylinder pump and the double cylinder pump, or we can have triple cylinders also. So depending on the requirement, we'll have the single cylinder reciprocating pump, double cylinder reciprocating pump, etc. So next, according to the existence of air vessels. So air vessels are nothing but smaller regions attached at the inlet on most commonly at the exit side of the reciprocating pump, in order to ensure that there is lesser amount of pressure variation. Suppose let us say this is the delivery line of the reciprocating pump. So this is the piston cylinder arrangement. So air vessels are attached over here. So these are called the air vessels. So which has compressed air separated by diaphragm. When fluid is supplied at a higher pressure, this air vessels takes some amount of pressure, thereby reducing the shock or the pressure surge on the delivery side. And when there is a pressure variation, or when there is a lesser pressure, so these air vessels compensate for loss of pressure by supplying back the higher pressure fluid that is retracted into it. So this is the function of the air vessel. So with the presence of air vessel, we have one kind of reciprocating pump, and without the air vessel also we have reciprocating pumps. So let us discuss what exactly is the single acting pump. So here in this picture, we are able to see a single acting reciprocating pump. So in simple, we can say a single acting reciprocating pump comes in contact with fluid on one side of the piston only. So this is the key word here, on one side of the piston. So here we have the piston, so it is coming in contact with the fluid on only one side. So this the other side, it is not having any contact with the fluid, it is completely sealed by the piston rings. So it comes to contact with the fluid on only one side. So during the 360-degree rotation, the half rotation, that is 180 degree, is the suction stroke, and the next 180 degree is the extension or delivery stroke it is called as. So this is the suction stroke and this is the delivery stroke. So for one complete rotation we have only one delivery. So for one complete rotation, one delivery in a single acting pump. It has one suction and one delivery for 360-degree rotation, or one complete rotation of the crankshaft has one suction and one delivery. So for one complete revolution of the crank there are two strokes, that is one suction and one delivery, and for one complete revolution we have only one delivery stroke. So next we have the double acting reciprocating pump. As the diagram represent, the double acting reciprocating pumps comes in contact with the fluid on both sides of the piston. Here we have the piston cylinder arrangement, piston connected to piston rod. So here the fluid is in contact with the piston on both sides. So here on the piston side as well as on the piston rod side. So when the piston rod extends on one side, it pushes the fluid into the delivery line on one of the delivery line. On the other side, it is performing an extension stroke on the left side. So it is pulling some fluid into the cylinder. Parallelly, it is doing both extension as well as retraction, that is suction as well as delivery. When this suction side on the right side, when the delivery is completed, again it moves back or it extends, pushing the fluid collected on the left side to the delivery line, thereby performing a suction stroke on the left side of the pump. So thereby doing two works simultaneously. It performs delivery, at the same time it sucks fluid on the other side of the piston, and vice versa. The process completely repeats. For one complete revolution of the crank there are 4 strokes. So whereas in a single acting pump we saw there was only 2 strokes for one complete revolution, in double acting pump we have complete 4 strokes for one complete revolution of the crankshaft. So there are 2 suction and 2 deliveries. So for one complete rotation, here the double acting pump performs 2 delivery strokes. So for one complete revolution it performs 2 delivery, whereas in a single acting pump there is only 1 delivery per revolution, complete revolution of the crankshaft. Each stroke has a delivery stroke. So let us try to find out the discharge from the reciprocating pump. So the discharge depends on the volume. The discharge is nothing but the volume flow rate. The volume of the fluid discharged is directly depending on the volume of the cylinder. So we are more interested in the size or the specifications of the cylinder. So A is nothing but the area of cross section of the piston in meter square, and L is the length of the piston stroke in meters. So area multiplied by length will give the volume of the cylinder, so which says the volume of the fluid that is being discharged, or volume of the fluid that is being admitted into the cylinder per stroke. So N is the speed of the crank in revolutions per minute. So R is the radius of the crank. So we have Q, the formula for discharge is L into A into N divided by 60 for a single acting pump. So here we have to understand, so area multiplied by length, that is area of the cylinder when multiplied by length will give the volume of the cylinder. So this volume of the cylinder is equal to volume of the fluid that is being sucked inside and that is being delivered simultaneously. So this when multiplied by the revolution, because the crank is continuously rotating, with this when multiplied by the speed, so it will give us the discharge, the continuous process discharge in meter cubes per second. Since this is single acting pump, we have one delivery per one complete rotation, one delivery for 360 degree, that is one complete rotation ge. So one delivery stroke irutte single acting pump nalli. So ide double acting pump tagondaga, so one complete rotation ge ಎರಡು delivery irutte, hence the same formula changes to 2 times LAN divided by 60. So for a double acting pump, since it has 2 delivery strokes, so it has 2 delivery for one complete revolution, the formula gets multiplied by 2, so the discharge gets doubled up. Coefficient of discharge. So it is defined as actual discharge divided by theoretical discharge. So the theoretical discharge, we have seen the formula. So Q equal to LAN divided by 60 for a single acting pump. So what is the difference between the theoretical discharge and the actual discharge? So actual discharge is not similar to theoretical discharge because of the concept called slip. So there occurs slip in many formats. So it may appear in the suction as well as during the performance of the delivery stroke also. The few of the fluid components get slipped away or which may not be carried out into the delivery line, and also the cylinder may not be completely filled, so it will have certain volumetric efficiency with it. The volumetric efficiency of the reciprocating pumps are even though higher in the range of 98 and 99. So there are losses wherein the cylinder will not be completely filled with the fluid during the suction stroke. So all this leads to the difference between the actual discharge and the theoretical discharge. So the ratio of actual discharge to theoretical discharge is called as the coefficient of discharge. So the slip we define as very simply, so the theoretical discharge ಏನು discharge ಆಗಬೇಕಿತ್ತು ಬಟ್ ಏನು discharge ಆಗ್ತಾ ಇದೆ, ಇವೆರಡರ ಮಧ್ಯೆ ಇರುವ ಅಂತರನೇ ನಾವು ಸ್ಲಿಪ್ ಅಂತ ಹೇಳಿ ಕರಿತೀವಿ. ಸೊ ಸ್ಲಿಪ್ ಇಸ್ ದಿ difference between the theoretical discharge and the actual discharge. So slip na percentage form nalli express madodadre, so slip divided by the theoretical discharge multiplied by 100 will give us the slip in terms of percentage. Power required to drive the reciprocating pump. So reciprocating pumps na drive madadike what is the power required? So power required is rho g h. H is nothing but the manometric head. Yava head ge nanu water na supply madbekagide, that is the manometric head, H is. So it can also be replaced with static head. Static head is HS plus HD, suction head and delivery head. Yavaga losses namge ಏನು ಗೊತ್ತಿರೋದಿಲ್ವೋ, so we can have this HS and HD. So apart from that, H represents the manometric head only. So power is equal to specific weight multiplied by discharge multiplied by the manometric head of the water gives us the power required to drive a reciprocating pumps in terms of watts. So let us have a look at a simple worked example. A single acting reciprocating pump having a bore of 150 mm diameter and stroke of 300 mm length. So here we have the single acting reciprocating pump. Single acting pump anta helidre, so one delivery per one complete revolution. One revolution ge one delivery stroke irutte. So size of the cylinder kottidare. So here I have the size of the cylinder. So this is the piston and piston rod. So the diameter of the cylinder kottidare 150 millimeters. 150 millimeters is the diameter of the cylinder, and the length of the stroke. So the length of the stroke, the maximum length that a piston can retract or extend, so that is called as the length of the stroke, that is 300 millimeters or simply 3.3 meters when converted into meter. Discharges 200 liters of water. So it has been given that a single acting pump with certain specification discharges 200 liters of water. So when the problem says about the discharge, it is nothing but Q actual discharge. The theoretical discharge we have to find out. Q actual is equal to 200 liters of water per minute. So 200 liters per minute, we have to convert it into meter cubes per second. So we have to convert it into meter cubes per second. So hence divided by 1000 by 60. So 200 liter pump discharging 200 liters of water per minute at 40 rpm. The speed of the pump is given. We have to find out, calculate the coefficient of discharge CD and the percentage of slip. So in order to find out the coefficient of slip and the percentage of slip, what I need is, I need theoretical discharge and the actual discharge. So theoretical discharge we have to calculate, but the actual discharge is given in the problem, that is 200 liters of water per minute. So in order to find out the theoretical discharge, I know the formula. Since it is a single acting pump, it is given by LAN divided by 60. So L is the stroke, it is given directly as 300 mm. A is area of cross section of the cylinder. Diameter is given. I can find out the area using the formula pi by 4 d square. And N is the speed of the pump. It is given directly 40 rpm. So with this basic details, I'll be able to find out the discharge theoretical discharge of the pump. So The given parameters are the diameter of the cylinder, that is bore of the cylinder, that is 0.15 meters. Length of the stroke is 0.3 meters, mm converted to meters. The actual discharge is 0.2 meter cubes per minute. So 200 liters per minute ಅಂತ ಹೇಳಿದ್ದಾರೆ. So it has been converted to meter cubes per second ಮಾಡಬೇಕಾದ್ರೆ we are dividing it by 1000 and by 60. So in order to convert minute into seconds, we are dividing it by 60. So hence we are obtaining 0.0033 meter cubes per second. We can express it simply in terms of exponent also, in terms of 10 power also. So the speed of pump is 40 rpm. So we know this basic details. So with this we'll be able to find out the area of the pump given the diameter pi by 4 d square, which will give 0.01767 meter square. Area of the cylinder, we know the formula in order to find out the discharge for a single acting pump. It is LAN divided by 60, multiplying the value of LA and N over 60, I'll be getting the value of theoretical discharge as 0.00353 meter cubes per second. So coefficient of discharge is given by the ratio of actual discharge by theoretical discharge. I know the value of actual and theoretical discharge. So on dividing those, I'll be obtaining the coefficient of discharge as 0.95. So it is unitless, because the unit of Q get cancelled out in numerator as well as denominator. Percentage of slip can be expressed as the difference between the ratio of difference between the two discharges divided by the theoretical discharge. So I'll be able to obtain the percentage slip as 6.5%. So it is hardly a matter. So the percentage of slip is only 6.5%. So the next worked example is a double acting reciprocating pump. So here itself we should separate out, it is a double acting reciprocating pump. So when we say double acting, there is two delivery stroke for one revolution. For one revolution there is two delivery stroke having a piston area. So it is directly given that area is 0.1 meter square. So in the previous problem diameter was given, here area is given as 0.1 meter square and stroke is 300 millimeters. So L is given 300 millimeter. The pump discharges 2.43 meter cubes per minute of water. The discharge, actual discharge is given 2.4 meter cubes per minute of water per minute at 45 rpm. Speed of the pump 45 rpm through a height of 10 meters. The head is also given, so monometric head. So through a height of 10 meters water is being supplied. Calculate the slip of the pump and power required to drive the pump. So we have to find out the slip na calculate ಮಾಡೋದಕ್ಕೆ ನಮಗೆ theoretical discharge ಬೇಕು, actual discharge ಬೇಕು. So theoretical discharge ನಾವು find out ಮಾಡಬೇಕು, actual discharge ನ ನಮಗೆ ಇಲ್ಲಿ already ಕೊಟ್ಟಿದ್ದಾರೆ. So theoretical discharge formula find out ಮಾಡೋದಕ್ಕೆ, since it is a double acting pump, we have to multiply our LAN divided by 60 formula with 2. So this 2 is because there is double means 2 deliveries per one revolution. So we are multiplying this equation by 2, we'll be able to obtain the theoretical discharge. So then we can find out the slip. So power required to drive the pump is given by the formula W into Q into H. So H is given 10 meters of water. So after calculating Q, so we'll be able to find out what is the power required to drive the pump. So the given are area of the cylinder 0.1 meter square, length of the stroke 0.3 meters, Q actual is 2.4 meter cube per minute. So dividing it by 60, will be obtaining 0.04 meter cubes per second. Speed of the pump is 45 rpm. The head of what monometric head is 10 meters through which the pump has to supply the water. So theoretical discharge is given by formula 2 LAN by 60. 2 is for double acting, that is 2 deliveries per stroke for revolution. So on multiplying 2 times the on multiplying 2 along with this, so we'll be able to obtain the value of theoretical discharge. L value, stroke value 0.3 meters and the area value 0.1 meter square and multiplied by the speed. So we'll be able to get the theoretical discharge 0.045 meter cube per second. Slip is given by the difference in theoretical and actual discharge. Actual discharge is given in the problem. So theoretical discharge is 0.045 meter cubes per second. On subtracting, we'll be getting the slip as 0.005 meter cubes per second in terms of discharge. So the power required to drive a reciprocating pump is given by formula P equal to W into Q into H. So W, we know the specific weight of the water, 9.81 multiplied by 1000. So 1000 has been avoided in order to get the power in terms of kilowatts. So Q is 0.045. So the theoretical discharge obtained is 0.045 multiplied by the head of the water, that is 10. So we are getting the power of the pump as 4.41 kilowatts. Power required to drive a pump is 4.5 kilowatts. So thank you all for your patience. And so you can watch all these videos in our DTE Studio channel. Can be browsed through our DTE website, dt.kr.nic.in. So any questions?